Integrals show up in physics in many, many places. And many of the examples of this actually come from sort of one main idea. To just sort of introduce the theme for this section on physics, I want to look at one example of that, which we're sort of already familiar with, which is velocity, the relationship between velocity and position. So, we know that if you have a position function and you take its derivative with respect to time, you get velocity. And if so, by the same token, if you integrate a velocity function, you get a position function. But there's another way to sort of look at where this relationship comes from, and it involves the equation that you've probably seen before, that distance is velocity times time. Well, this equation is true, but it comes with an important caveat, and that is, for this equation to be true, the velocity must be constant over the entire interval of time through which the object is moving. If you have an object that's speeding up or slowing down as it moves around, then the velocity is changing. And if your velocity is changing, this equation doesn't work anymore. So how can we fix this issue? Well, the general idea is if your velocity is a function of time, so it's not constant, then what we need to do is we need to shrink the interval of time in this equation down to be so small that the velocity doesn't have a chance to change. Because if the interval of time is so small that the velocity is essentially constant, then we can use this equation again. So we need to pick an interval of time that's really, really tiny. Well, any finite length of time, the velocity might change. So we need to choose an infinitely small length of time, and that's dt. Right? dt is our name for an infinitely small amount of time. The distance traveled at time t is v of t times dt. So this gives us an infinitely small little displacement that the object moves through at a single time. To get the total displacement, we just need to take all of these infinitely small little displacements, v of t times dt, and add them all together. And of course, it's an integral that does that, and you might have bounds. So what we did here was we started with some sort of physical equation that was true only if everything involved is a constant, to handle the situation where things aren't constants. We break it down into infinitely many infinitely small pieces. In the infinitely small pieces, everything is a constant just because everything is so small that it doesn't have time to change. So when we have it in these infinitely small pieces, we can use our constant equation, and then we assemble the infinitely small pieces back together into a full solution by doing some sort of integral. You can actually do this with any equation where everything involved has to be a constant. So we're going to look at a few different examples of that.